Okay. So we might as well get started here. So I'm going to try to cover two things today. And I've got handouts for those of you that are online. You can, these are right out of the FE review manuals. And I can, I've got them if you want to come by my office and grab them. So we're going to do two things tonight. One is construction management, and the other is surveying. And the issue with both of these, for Carroll students at least, is that you don't have classes in either of these. Josh, I don't know if you...
I don't know many engineering schools that actually do have.
You have it. I know it's kind of a weird trend.
And I went to an engineering school and I don't agree enough with it.
Yeah. So the main purpose of this is to give you at least some ideas of looking at some of these problems and recognizing them, that maybe you can get some points. And I don't claim to know a lot about what we have, but I'm gonna look at the thing that you have there. I was gonna go through, first of all, on that handout that I gave you, it has construction management on it, and on the bottom left or bottom right, it says problem 52 under construction management. There are just some things that are so interesting about this, because I really don't know this myself, but it gives you that chart and it says, what is the following type of chart called? And they give you these, and I don't know, did I circle the answer on yours?
There's a bunch of triangles.
There's a bunch of triangles. So what would you guess that would be? A triangular bar progress schedule, and that's exactly right.
Yeah.
And you go to the next problem on the next page, problem 53. It asks, what kind of chart is this? And it really kind of comes down to the top two. It's either a bubble chart or an arrow chart. But then if you look at the one below it, that's a bubble chart. So the one that's above it that has the arrows on it, it's an arrow activity on arrow network. So, and those are the correct answers. So I'm thinking you might be able to have an educated guess about how to do some of these things. So I have not had formal training in construction management and laying out, you know, a construction flow chart and understanding the construction time and the critical path and everything like that. But this at least can give you a little bit of information for that. Let's see here. I want to see what I have laid out for these problems here. Oh, this is a different one. Okay. Oh, okay. Now I can do it. So let's on that same page, it's problem 55, and they provide you with a flow chart that they've got, and it looks like this. I'm gonna lay out, or I'm gonna be out of bounds here. So this chart at the start, and then it has these activities, and they lay these activities out like this: A8, B5, and C7, and then further out they have D9, and then 3 and E3 H1 and then end. And all of these are circled. So each one of these letters represents a construction activity. So there has to be some knowledge about what that takes. The number below it is the duration that each one of those activities takes to complete. And they do connect them in a way that where it's understood that the path that you follow for these connections indicates what activities have to be done prior to other activities. Let's see here. This one connects straight to here. For instance, activity D can't be started until activity B is finished. Okay, so you can see, but activities A, B, and C could be completed at the same time. They can start whenever you need to have it start. Okay, so some of them are dependent on the others. You can lay that out. So what they ask in this problem is, what is the critical path? And I'm going to go through this once. Unless you're really familiar with it, it's kind of an onerous type of activity. If you and so the paragraph after they give you the problem explains how they do that. But the table that they set up on the next page is what really explains it all. So I'm going to write this out as quickly as I can. Okay, so understanding what these means are pretty important. So here's the activity that we have, and we'll list it out: A, B, C, D, E, F, G, and H. Okay, D is duration, and that's given on the chart that you're given for the problem. So it's 8, 5, 7, 9, 3, 3, 5, 1. Okay. So now these other acronyms. EST is earliest start time. EFT is earliest finish time. LST is latest start time. And LFT is latest finish. And TF is total float time. And it'll become obvious here how they do this. Okay, so earliest start time is identified as what day on which is it possible for this to start. So all of these activities, A, B, and C, start at day 0 because there's nothing in front of them. D can't start until B is completed, so the earliest it could start would be on day 5. E, same thing, day 5, can't start before that. What else do we have here then? F, it can start after 2 of those paths, but the earliest start time would be if it passed through activity A. So the earliest that it could start would be day 8. Am I doing that correctly? I'm not, am I? No, I'm not. It's the latest. Okay, so that's interesting that they have it. So they take the longest path between the 2 that get to that point. So they're saying day 14. 5 and 9 add up B and D before F. Okay, G, where is G?
Between B and N.
Did I miss that? Oh, okay, here we go. G, and what's the duration on that? 5? Okay, G is earliest it can start is 5 days into it, and then H is right here. So you take the longest path, and it looks like that's 8. Then that guy. Okay, earliest finish time. All you're doing is adding the duration to the earliest start time. So for this case, it's easy. 8, 5, 7. But when we get to D, the earliest finish time you can have is 14 days. E is 8, F is 17, G is 10, and H is 9. Okay, now it gets a little hairy, and I was trying to review this before you guys got here. What you end up doing, the latest start time is actually calculated backwards from the latest finish time. So on the back, if you turn back a page, it says that determination of the latest start time and latest finish time for an activity is done by a backward path through the diagram using the maximum project duration as the starting point. So in determining the latest project duration would be to go along the path that has the longest time in order to get to the end. And that would have to pass through B, D, and F. So we have 5 plus 9 is 14 plus 3. That's 17 days as the latest finish time that we could have. And let's see here. How do they determine and which ones get? Oh, okay. That would then apply to, let's see here. Is the minimum latest start time in the activities that follow or that are following it. So the latest start time for these last 3 activities is the longest or the latest, I'm sorry, the latest finish time for all of these activities at the end are the same because there's nothing that follows it. So they write in here that the latest finish time for these last 3 F, G, and H is 17 days. Okay. Let's see here now. Why is that though? So now I have to read here. Activity D is proceeding. Okay. Accordingly, okay. All the activities preceding the project finish are all day 17, since no activities follow them. Okay, so we listed those. The latest finish times of activities G and H are day 17. That means then we can calculate the latest start time of those activities by subtracting the duration from the latest finish time. So for F, let's take an example. The latest finish time is 17 and its duration is 3. So the latest start time it can have is 14. For G, 17 is the latest finish time and its duration is 5. So its latest start time is 12. For H, 17 minus 1 is 16. Okay, now it says, if we go to the next layer, like activity D, it's not preceded by activity F. It's followed by activity F. So its latest finish time is the latest start time of activity F. Okay, so the latest start time for activity F is 14 days. That means that the latest finish time for activity D would have to be 14 days. So if we go over here to activity D, we're going to write in 14 at that point. Okay. Those latest start time is 14 minus 9, so that's 5 days. All right, let's look at another one. Activity E. It's followed by activity H. And activity H, the latest start time is 16. So we're going to put that as the latest finish time for activity E. So this is 16. Let me get that here. Yeah. And then we take 16 minus 3, which is the duration, its earliest start time, or its latest start time is 13. Okay, we'll move up to the next layer. Activity A is followed only by F. The earliest start time of F is 14. That means that the latest start time of F is 14. The latest finish time for A is the same thing. And its latest start time, 14 minus 8 is 6. Okay, let's do C first. C is followed by H. The earliest finish time for H is 16. So that's the latest finish time for C. 16 minus 7 is 9. That's its latest start time. And with B, it's followed by all of these activities. Let's see how they do B. The latest finished, so it is followed by G, and let's see here. It has to go through all these different kind of paths. It says for B, the latest finish time is 5. How do we calculate that? The latest start time for 5 is, or latest start time is D, which is right here.
9 plus 3 is 12, 17 minus 12 is
5. Say again.
We start with the latest finish time is 17, D plus F, so 9 plus 3 is 12, 17 minus 12 is 5. If you have to take the longest path to get from B to the end.
Right, yeah, so it does have the longest path. So the latest start time for D is 5. That makes it's the latest finish time for B. 5 minus 5 is 0. Okay. So now you determine the total float. It's either subtracting the earliest finish time from the latest finish time or subtracting the earliest start time from the latest start time. Either way works. So let's do the earliest finish time from the latest finish time. So 14 minus 8 is 6. And we'll just carry out these calculations. 5 minus 5 is 0. 16 minus 7 is 9. 14 minus 14 is 0. 16 minus 8 is 8. 17 minus 17 is 0. 17 minus 10 is 7. 17 minus 9 is 6. Oops, did I do that incorrectly? 17 minus 9 is 8, sorry. Guess I better brush up on my math skills. Okay, so what does that mean? Total float means what kind of leeway do we have in finishing these activities? If your total float is 0, that indicates a critical path. Okay, so anything that goes through B, D, and F is the critical path for this. So the critical path for this project would go through B, D, and F, and then the end. Okay, the other activities you can put off for a few days and still finish before the last day, the 17 days that you needed to get that done. Okay, so total float means how much leeway do you have? If it's 0, that indicates a critical path. Okay, so the critical path are the activities that you need to finish in order to finish the project on time. Now, do you want to do that for an FE problem? Quite a while. It would take you a good number of minutes to actually figure that out. But what they tend to do in the exam is that once they give you this, then they ask you different questions related to it. So one of these probably covers like 3 or 4 questions. And
Wait, so they give you this information?
no.
Okay.
If you go to like starting on the page that has on the bottom 52 on the bottom right corner, that's a practice exam. That would be typical of what you would see on an exam. And this same problem that we just did, if we go to, okay. On the next page, hopefully, wait a second. Oh, problems 53 to 55 are based on the following information. Exactly the same chart we worked here. Okay, so it's the same information, but then they ask you these questions. They say, the earliest date this project can be completed is, oh, they give you a, so it starts on January 1. And they give you, they ask you, what's the earliest date this project can be completed? So you're looking at 17 days of total construction. And here's the odd thing about construction is starts at January 1 is day 0. Okay, and we know that the maximum duration that we have on this project is 17 days. So January 17th would be the earliest that it could be finished. Let me make sure that I've done this correctly. Yeah, yep.
Just a coincidence too, but the critical path is the 17 days.
Yes, yeah.
So would that be?
Yeah, absolutely. Yep. So, right, if you wanted to find out really quickly what that was, you could kind of glance and see, well, if I connect the dots, what's going to give me the longest days? And that's the critical path.
Okay.
Yep. Because at the end, then you don't have any float at that particular point. Yep, that's great. It says total float for activity A should be 6. Let me just check real quick. So I'll go back to the answers here. See? Yep. And then it says the latest day that activity E can start is, so you look at activity E, the latest day that it can start, latest start date for activity E, January 13th. So it'd be B. Okay. So you can knock out 3 problems using something like this. Anyway, I think, that's really kind of all I was going to cover on this. There are other things that I just don't know about. Like if they give me number 60 on this page that I'm looking at, which is like 63. The Ashdow structural number equation can be rearranged to solve for surface thickness D1. I wouldn't know how to do that. I don't know. Do you guys, does everybody know what Ashdow is? You probably do, Josh.
I have no clue what it is.
It's actually the something American Association of something transportation, state, okay, yeah. I don't know, did you guys cover that in transportation at all? Okay, so maybe you would know some of these things.
Yeah.
Yeah, the main thing I was gonna point out for these was that they'll ask you what kind of a chart it is.
Yeah.
Based on the shape and things, it's like, well, I could probably guess at what that actually is. And then just this whole critical path deal here. And what you pointed out is great, Ashley. You just add up the line, that's your critical path. And you can mark that. Okay. That's all I was going to cover on construction management. That's all I know. Seems like the problems that they give really kind of center around that in that practice exam that they give you. Oh, you know what? I'm not even, that AASHTO problem, that's not even a construction management thing. It's actually a materials question, I think. Okay, so let's move on to surveying. So I gave you guys that little survey handout. I need to get to the right spot and where I want to be here. What's on the cover of your survey handout that I gave you? Okay. Okay, does that have geometric design? Is that what's on there, the top? Or no?
Looks like a
Practice exam. Okay, all right. The right page. Okay, here we go. All right. Let's look at this. On this practice exam. Wondering what I have covered. Now I'm not finding where I'm actually. Okay, so on your handout, let's see, I need to get to the right spot here. Sorry for delaying here. How big is your handout? Just fairly small? Just trying to find what I've got. Oh, here we go. Sorry. Get organized.
That looks like it.
Thanks. Okay. Okay, here's what I want to do. I think let's go to the sheet that says number 48, lane surveying. You guys have that one? Yep. Okay, all right. So in the transportation stuff, usually, or most of them seem to be either geometry problems where you're laying out a curve, or earthwork quantity type calculations. So on, let's see, how do I, oh gosh, is that the right one? I'm groping here. Sorry, guys. Where are my calculations that I have for that? I'm wondering if I got it mixed up in these. No. Okay. Geometric design. All right, well, let's okay, you have a sheet that says practice problems on it, like this?
Yeah.
It's like the very first page.
No, no, I'm gonna give you these then. This I know we can do. We'll get to some of these. So, a lot of what they use is like the average end area method to calculate volume of cuts and fills. They might throw a real odd thing, and I can't remember what they said. There's like one in there that they say, use the Simpson rule or something like that. And I'm pretty sure if you went into the reference manual that you could probably find that formula, but I didn't know it offhand. But most of the time, they're fairly straightforward types of calculations. So if we look at that one that you have practice problem, let's do the first one. Now they eventually give you the answer, but we can work it out here. So this would be typical of what you would find on a road job, let's say. I don't know, what type of engineering do you do, Josh?
I'm in land development.
Well, okay. But if you're doing land development, you've got a street. Street usually has a center line, right? You've got stationing, depends on where you go. It could have some cut and fill, etc. And do you work with Civil 3D? Okay. And you use that to calculate, do quantity calculations?
As soon as I learn how to do that.
I got you. Okay. All right. This is where you would actually come up with. So usually, when you have a center line calculation, they've got the engineering designation for distances, and it's a number plus another number. And they are referred to as stations. And in this particular problem, these are in meters, which you will never work in unless you move to Canada. But these are the stations that you have: 20 plus 00, 20 plus 10.5, 20 plus 21.5, 20 plus 28.45, and 20 plus 40. Okay, so these designations mean the number on the left side of the plus sign is actually hundreds of feet. The number on the right side are feet. So the actual number for this would be at 2,000 feet. For the next one, it would be 2,010.5 feet, 2021.5, etc. Okay.
Why do they write it like that?
That's a good question. I don't really know why. It's the designation that they identified for it. But at each one of these stations, they've identified a cut area. This is, I'm going to write area. They don't tell you explicitly, but they do give you the dimensions of a meter, or the units of meter squared. And they also have fill in square meters as well. And they go through. So cut, the last three stations have cut. This is 14.32. The next one is 64.73. And the next one is 187.42. And then fill, first one is 173.21. 43.56, and then the last one is 9.63. So station 20 plus 21.5 has fill and cut associated with it. And what it asks in the problem is the total volume of fill required for this section of road is most nearly, and they give you the answers in cubic meters. So I think in most cases, if you use the average end area method, it would work out fairly well for you. So if we're looking at fill and we're doing the calculation for it, what average end area means is, if we just write this out here, average area means that you're taking the average between the fill at this station plus the, or plus this and dividing it by 2. So it's 173.21 plus 43.56 divided by 2. And then you multiply it by the length between those. And in this case, the length between the two is 10.5 meters. Okay, we can write this out. What I get for that? Oh, I didn't exactly do that. I'm not going to give you that. So, but once you do that, you end up with a volume that exists between these two sections here. And I'll tell you what I got. I got 1138.042 cubic meters. Okay, we do the same thing like down here. We've got 43.56 plus 9.63 divided by 2. The length between these two sections is 2010.5 minus, or the 21.5 minus 10.5. So it's 11, right? 11 meters. Okay. And if you calculate that, you get 292.545 cubic meters. Now, the other thing is that you've got fill here, but none on the next station, but it's essentially zero fill, and you would need to take the average of those. So it's 9.63 plus 0 divided by 2, and you're multiplying it by the distance here. Let's see, 28.45 minus 21.5. Ashley? These two. Okay. And I get a volume of 33.464. And if you add them all up, I get 1464 cubic meters. And what are the answers that they give you? Most nearly, I believe it's B. Okay. Now, the other thing that they recommend you do, instead of this average end area method, it's not very accurate when you do it this way. They say you could use what they call the pyramid calculation. And it actually, like here, you could use where it's the distance 6.95 times the difference in areas here, which is 9.63, and divide it by 3. And if you do that, it comes out to be 22.3. And if you plug it into that, you get a value of like 1452. So it's closer, but you get there with the average end area as well. Okay, so you don't necessarily have to do that.
So if they hadn't asked for the average, ask for the volume of fill, could it ask for the volume of cut and you could do the same thing?
Absolutely. Yep, exactly the same method. As a matter of fact, I'm surprised that they don't have the next question. Yeah, they do the same thing. Total volume of cut required for this section of road. You do the exact same thing. Yep. Okay. So that's how that works. Pretty simple calculation. If they give it in English units, here's what they might do. You would have stations in feet, you'd have your cut area in square feet and fill in square feet. but the answer they might ask you in cubic yards, right? So when you calculate it all out, you're gonna get cubic feet. Then what do you do with that to get cubic yards? 9 times 3, actually 3 by 3 by 3. So it's 27, divide by 27, and that'll give you then cubic yards for it. All right. Now what do I want to do? I think I really want to do that one. The next problem that they have there is they talk about, go to the page that has problem 2 on it. Oh, I'm sorry, problem 3. It says problems 3 and 5 are based on the following information in the illustration. And they give a couple of points, and they ask you, they say, this is a vertical profile for a airport runway. And they then ask you these questions for it. And they say the minimum required length of vertical curve at the point of vertical intersection is most nearly, give you all that. If you have that kind of background, it seems to be really specific to airports in this particular one. So unless you know it, I'm not sure I would tackle those things. Let's see what else we wanted to do here. 4 and 5 are really specific. Number 6.
Do like for these sections, since we don't have a super strong grasp, are we just doing our best educated guess?
Yeah.
For this?
Yeah. Yep. I mean, you guys did vertical curves in transportation, right?
Yeah.
So
yeah, so we did that.
it might, you know, you might have enough knowledge to be able to do that. I'm not super well versed on that. So, okay. I'm going to go to problem 6 now. And problem 6 deals with northings and eastings. Are you guys familiar with that?
I've heard terminology, and that's about it.
Okay, all right. The concept is actually really easy. Because you're really envisioning a grid. And a northing refers to its position in the north-south direction, and an easting refers to its position in the east-west direction. So in problem 6, they ask you the north and east coordinates of point B for the situation shown are most nearly. They give you 2 of those, and then they give you some more information related to it. Okay. So A is over here. This is A, and it has a northing of 1,300 meters and an easting of 850 meters. Okay, so if you imagine a grid that looks like this, and let's say your origin is right there, and you go up a certain distance to get to northing, and then you go east a certain distance to get easting, your dot would hit right there. Okay. So it's usually, if they give it like that, that's like a local datum. Somebody established this for a project, and you just know that, okay, that's where it sits. But if everything is relative to that, you're okay, right? It doesn't really matter. You don't have to tie into a USGS geodetic survey point or benchmark or anything. So they also give you information for C, which is up here. And it says that it has a northing of 1800 meters and an easting of 900 meters. Okay, and they give you a solid line between them. And this is labeled as line C. Then somewhere here, they identify point B. And in the diagram, let me just tell you, they'll try to trick you on these things. In the diagram, they give you point B, and they ask you what is the northing and what is the easting, and you're supposed to find that out. But then they have these connecting lines that are dashed to it. This one is labeled B, and we know the length of it is 430.116. And A has a length of 390.512. Oh, and they're all in meters. These are meters. Okay. So you got to get to B somehow. All right. They don't give you a distance, but you can figure out a distance, right? We know that northern and easting at A and C, you can figure out a distance for that. Okay, so it's the ratio of those, the difference between them. So let me do this in a different color. So if we go up here and then over to here and create a right triangle on this, the northing difference is 500 meters. It's 1800 minus 1300, right? Going up 500 meters to get to 1800 meters as a northing up there. The easting is 900. This is 850. That's a little deceiving. This is only 50 meters here. So we can find the length of line C. C is equal to the square root of 500 squared plus 50 squared, right? And what is that value? Oh, yeah, I'm good. I got 502.494. So you have to be pretty precise on these things in order to get to where you need to go. Okay. Here's the thing also. Let's see. How do I want to put this? Okay, we're going to figure out then the angle. Let's see here. Going up like that. Going like this angle here, which is theta. So we can calculate theta. Theta is equal to, let's see, how would I calculate that? Theta is equal to the inverse sine of 50 over 502.494. Do you guys agree with that? It could be the inverse cos of 500 over 502.494 also. But just for kicks, what do we get for that? I'll tell you. I got it. Never mind. 5.71059 degrees. Pretty small angle. And the way that they show it here, it's really deceiving, right? The way they show it is no way that's as small an angle as what they're talking about here. So yeah, okay. Just for kicks, what actually calculate the inverse cos of 500 over 502.494.
Same thing.
Okay. Just wanted to be sure. Okay. So it's actually turned up kind of like that. So it's a little bit deceiving for what we're actually trying to get. Okay, so with that, then, how do we get to B? Yeah, I'm trying to remember how to actually go about doing this. Let's see. Oh, okay. Here's what they do. We can calculate the angle here between this line C and B because we know those, right? But how do you know the law of cosines?
Not on top.
I don't either. So if we take this at, let's just call this alpha here.
My question is, wouldn't that just be 90 minus the 5.71?
No, because the way they've drawn it is really not, it's misleading for you. Here's the way that it actually goes. It actually has, so we've got this, here's A, here's C up here, and we calculated out, this was 500, this was 50, and this was the line C right here. And we calculated this angle as 5 point blah, 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 right, degrees, whatever that was. Because we're dealing in northings and eastings, if we figure that out, this is facing directly north. Okay. Now we've got this other angle here that goes actually up to here and over here to B. We know the length here, we know the length here. And if we draw a right angle to our northing, the sum of those angles, this 5 plus this angle here, plus this angle here, have to equal 90 degrees. But getting this angle, this alpha, is a really hard thing. And so here's what they say in the book. If you use the law of cosines, it says that alpha is equal to the line b squared plus c squared minus a squared divided by 2bc. I would never remember that in a million years. The thing is, we've got all those lines in there, and if you plug those all in, you get alpha is equal to, wait a second. Oh, sorry, I miswrote. This is the cosine of alpha is equal to that. And it says that the cosine of alpha comes out to be 0.6593, and that means that alpha is equal to 48.75349 degrees. 48.7539 degrees. This was 5.71059 degrees. And that means then that this 90 degrees thing here, we got that. This is going to be equal to 90 minus 5.71059 minus 48.7539, and that's equal to 35.53592 degrees. Isn't that a kick in the pants? Okay, why do we care about that? Because in our little diagram here, we've identified now this angle. Okay, we got alpha. Then we got this, which was 35 point blah, blah, blah degrees. And we know that when we project this out, it runs along the east-west direction because this is the north-south, and we've figured out this is a right angle, and we can go a right angle triangle to point B. We know this angle and we know the length of this line. This line is 430.116 meters. And we can then calculate this horizontal distance, which would give us our easting, and this vertical distance, which would give us our northing at that point there. And if you do that, you end up with here, the northing is 1550 meters and the easting is 1200 meters. That's a long one. That's a tough one. Yeah.
So it seems to me like the options that they give you though,
What do they
there's
give
only
you?
one logical answer.
What are you saying?
That is true.
The options that are given, D is the only logical answer.
Because the A is at 1300, so then B would have to be,
Like B clearly can't be south of A given the distances, which means that D is the only answer.
Yeah. And that kind of thinking will get you far in the FE exam when you start to eliminate things. Me, I get bogged down in the weeds and I can't see out of them.
Well,
But if
yeah,
you can
if it
look-
wasn't so, if there were two reasonable options, you
Yeah.
have to do that.
Yeah, and you could also, you know that the easting is no way going to be less than 850. So the first two options are out for sure. So, yeah. Very good. Okay. Yeah. Yeah. Let's see. Yeah, we got a manometer problem. You guys want to do that? No, we already. You don't want to do that anymore. So let's also go to in your handout. There's your handout. There is a page that says geometric design. Get to that. Okay, here we go. 49, it says 49 and it has geometric design on it. And it gives you all these different problems. So let's see. These turn out to be geometry problems. And if you've taken anything in transportation, you know what they're talking about. Like in problem number 1, they give you an arc. Let's see here. Let me get this off here.
You said geometric design?
Yeah, you don't have that?
I probably will.
Do you see it, Ashley?
Oh, I do have it, yep.
Okay, all right. I just want to make sure. I do. Not give that to you. All right, so like on number 1, here's what they give you. So they have a curve, and if you know the terminology, it helps quite a bit. So they give you what's called a PC, which is what, Ashley? Point of curvature? Is that what a PC is? And they give you a station at which that occurs, 10 plus 46. So we've got this line coming up and it hits that point. That's when the curve starts. And then it goes through this curve that looks like that. And it ends up at a point out here that they call PT, which is the point of tangent, right? That particular one. And they give you these dimensions like across here, this, oh, they give you the length of the curve is 820 feet. And they identify this point out here. And they measure out this angle between that I, which is that the intersection point? I'm trying to remember terminology, is equal to 104 degrees 36 minutes. And it asks you, what is the radius of the curve? Now, I'm pretty sure that if you were to go into the reference manual, they would give you these formulas here. And what they say is that the radius of the curve times the sine of I over 2 is equal to the length of the curve divided by 2. So you can plug those in. There's some conversions you need to do. If you have an angle measured in degrees, minutes, seconds, this is in degrees and minutes. Do you know what those mean? That's, so yeah, there are 60 minutes in a degree. There are 60 seconds in a minute. So to convert that, you would have 104 plus 36 divided by 60. What's that? 0.6. Okay. So it's 104.6 degrees. Okay, so you can plug that in as I, and then you have the length of curve and you can calculate the radius. When I do that, I get, where am I here? A radius of 518.2. And what are the options that they give you? So it'd be A, 520. Okay,
That I, the 104 degrees, that is about like surrounding the center point of the curve, right?
correct.
Okay.
Yep. Right. So curves are typically identified by two endpoints. One is at the, and it's all has to do with stationing. So you start here at the point of curvature and you travel around here. They give you the length of that curve is 820. So if you had 820 to this station here, you would end up at your station at your point of tangency. So yeah, and they're giving you a radius. So this is a steady radius around here. It's not a compound curve or anything like that. Okay. Let's look at, let's see here. Okay, problem number 2. It helps to draw this out. They say a freeway route has a horizontal curve with a PI at a certain station and an intersection angle, intersection angle, okay. And a radius of 1760. So it looks something like this. So you've got this intersection point here, comes out to your point of curvature here. And it has a radius. So it's a standard radius and it comes out here. Oh, it's a pretty small angle. Okay, so I'm not going to go too far to your point or PT at that point. And we know that this I angle is equal to 12 degrees, 24 minutes, 0 seconds. Now they have a PI. So a PI means that you're running at a tangent line up from your PC out to here, and another one from your PT out to here. And it meets at this point up here that they call PI, or a point of intersection, at that particular point there. Okay. Let's see. And the station of that PI is at 11 plus 1.86. Okay, and they give you a radius. So this radius here is equal to 1760 feet. I'm going to give you an imperial units question here. Okay. They also say an intersection angle I at 12 degrees, 24 minutes, right, meaning that it moves in a clockwise fashion. Goes to, as you're looking at it, it moves to the right. Okay. So you can convert that I, and if you do that, it's equal to 12.4 degrees. Then there's also terminology here, if you know it. The distance from the PC to the PI is called the tangent T. And you can calculate that because you know you have this triangle really that goes, where is the triangle that we're looking for? It's equal to R times the tangent of I over 2. Oh, here, okay. So if we divide I in half, this angle is I over 2. And T is equal to R times the tangent of I over 2. And if you calculate that out, you're going to get 191.2 feet. And once you have that, you know this is, so we know the station at PI there, and you're going to move backwards to get to PC in order to get the stationing there. So PC would equal 11 plus 1.86 minus 191.2. And that comes out to be in, do they ask you in stations? Yeah, that would give you a stage. So this would actually be 1 plus 91.2, and that equals 9 plus 10.7. So you pick A. Yeah. Did you know that rule, or what this meant here, this tangent here? Ashley?
I'm not immediately, but now that we've gone through it, it's like, oh yeah, I totally remember this.
Yeah, the significance in this problem is that when you divide that I in half, then you create a right triangle that looks like this.
Mm-hmm.
And we're given this radius, we know what that is. And they're giving you the I. What else do you want to do? Oh, gosh, there are all kinds of different things here. Let me see if there's something else we want to do that's funner than that. I'm not seeing it though. So problem number 3 is a vertical curve. And vertical curves are, to me, are a little more complicated. And this will be the last thing that we do here. I'm not going to go into other details with it. Thing is too, I don't know how many problems you can expect on the exam in transportation. I'm not quite sure. They give you that, I'm sure.
Eight to 12.
Really?
Yeah.
Oh, crap, that's a lot.
But it also, it's like geometric design of intersections, which is what we're doing. But like traffic safety, traffic capacity, traffic flow, traffic control devices. So it's like transportation too, as well.
Right, yeah. So you would be much more versed in that than I would be. I don't understand that very well. Let's look at number 3 on that same page. We've got a vertical curve. So this vertical curve is defined by this line that meets at a point of intersection. And on a vertical curve, it's called a point of vertical intersection. And that is at station 87. And then it comes out like that. And I didn't draw that very well. Change that a little bit. So it comes out like that. Then there's a curve between it. So we start out here at the point of curvature here, but here they call it PVC because it's a vertical curve. And it goes through something like this. It makes a gentle curve and you end up at the PVT, point of vertical tangency, on the other end. I'm not sure what they mean by this. They tell us that the length of that curve, I guess, from here to here is 8 stations. Does that mean 800 feet? I'm not sure I know what that means. A length of 8 stations. Somewhere in here they explain it. What do I have on my notes here? Because I know I looked at it. Yeah, 1 station is 100 feet. Okay, so this is equal to 800 feet. Okay, so what they ask in this problem, vertical sag curve, blah, 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 blah. The elevation of the lowest point on the vertical curve is most nearly. So we're trying to find out what is the elevation at that point. Okay. So what else am I missing here? Oh, they give you the PVI elevation on here as well, which is equal to 2438 feet. Okay. Oh, they also give you the slopes of these lines that come out here. So this is a minus 2.0% slope. This is a positive 1.6% slope. So there, the flow of travel goes from left to right. And if you're going downhill in the direction, they're giving it a negative slope. It's going uphill in the direction of travel, it's a positive slope. All right, what else am I getting here? Okay. All right, we can figure out here, I believe, we know this, and we're going to then determine an elevation at the point of vertical curve. So if we go up from this point here, through that center there, and bring it out here, we draw this right triangle. And we know that this distance from here to here is half of that. So this is 400 feet. Now, the dimension that they give, it's not the length of the curve, I'm sorry. It is only the horizontal distance from PVC to PVT. So we know that, and we know this curve here. So we've got a triangle now that looks something like this. This is minus 0.2%. How do we figure out an angle? Oh, no, we don't need that. We know that if this is this dimension right here is 400 times 0.02, right? Because we're dropping 2%, 400 feet, and that equals, I don't know what that equals. Oh, it equals 8 feet. And we know this is 400 feet. Okay, this is the PVC. We know also that at this point, which is right down here, the elevation is 2438. And if we add 8 feet to that, the elevation at the PVC is 2438 plus 8, which is equal to 2446 feet. Okay, why did I do that? I have no idea. Let's see here. It might be close enough. Let's see, this goes on for quite a while here. No, that is not the answer, because we're trying to get the elevation at this point right here. So it drops, it has the curve drop down. But how are we finding that out? Oh, you know what? So this is misleading that I drew this on. This lowest point of the elevation of the curve is not going to be right in line with the PVI, because we have two different slopes here. It actually is over here somewhere. So we're trying to find the elevation at that point there. So it doesn't correspond with the distance at the PVI point. It's that particular point. But what they say, and I learned this just from the manual that we got, so we don't need this anymore. We got that. The distance from the PVC to the lowest point in the curve is what they call X sub M. And X sub M is equal to the ratio of, let me see here. It's the slope that they call G1 times the length of the whole thing, or L, divided by G1 minus G2. So G1 is equal to a negative 0.02. G2 equals 0.016. We got L, so we can calculate this up. It's a negative 0.02 times 800 divided by a negative 0.02 times 0.016. And if we calculate that out, we get 444.44 feet. So that's the horizontal distance to the lowest point right there. Now what do we do with it? Oh, then they have another question. Comes from the back, it comes from the reference book. It's the only way you could do it. They say then that the curve elevation is going to be equal to the Y of the PVC, that's the elevation. So if you try to figure this is Y and this is X here. The Y of PVC plus G1 times X, and it's XM at that point, plus G2 minus G1 divided by 2L. That's so weird. Okay, times XM squared. Good grief. You got to go to the reference manual and try to find that out. And they probably have little diagrams in there. Do you have a reference manual?
I'm looking at
Do
it.
they show it? So you could utilize that. If you plug in all those values, this is 2446, that's the elevation, plus a negative 0.02 times 444.4 plus 0.016 minus 0.02 divided by 2 times 800. And this is all multiplied by 444.4 squared.
Oh,
And the curve elevation is going to be equal to 2441.6. I'm sorry, 56. Where they give you 24, so it'd be C. So better way you can try to do that. We've got this. We know it's not going to be less than 2438. So you can eliminate the first two from that. So it's somewhere between there. Where's 2445? If you calculate this PVC, it's not going to be higher than that either. So you don't have to go as far as what I gave there. You could stop. Figure that one out. Okay. That's all I got. Is Lauren still with us? You left a long time ago.